Welcome to Module 4, Lesson 24. In this lesson, we're going to start talking about simultaneous equations. We've been talking about linear equations, we've been graphing them, finding solutions, and now we're going to talk about something called simultaneous equations, also known as systems of equations. Okay, we're going to start with this exercise where Derek has scored 30 points in a basketball game and did not go to the free throw line. What that means is that he only scored 2-point shots and 3-point shots. So what I want you to do is pause the video and list some combinations of 2 and 3-pointers that would total up to 30 points for Derek. Okay, so see if you can fill in the table with some combinations there. Okay, so as I look at this, I can see that if I give Derek 15 2-pointers, then that's his 30 points right there. So it would be 0 3-pointers. And I can do the same thing for 3-pointers. If I give him 10 3-pointers, that would be 0 2-pointers. Okay, now I'm going to look at some combinations, and maybe some of these are ones that you had. I noticed that if he gets 6 2-pointers, that's 12 points. That leaves 18 points that he needs, so 6 3-pointers would be the other 18 points. And here's another combination, 9 and 4. 9 times 2 is 18. 4 times 3 is 12, and that adds up to 30. And 12 and 2, 12 2-pointers would give him 24 points, and 2 3-pointers would give him 6 points, a total of 30. Same thing for 3 and 8. Now, if I want to write an equation for this situation, I would need to, of course, define my variables. So I would want to let x be the number of 2-pointers and y be the number of 3-pointers. Of course, you could have done it opposite. That would be fine too, but I need to define my variables so that my equation is going to make sense. And I noticed that every time I know the number of 2-pointers, I'm going to multiply that by 2. And if I know the number y of 3-pointers, I'm going to multiply that by 3, add those together, and it should come out to 30. So that's what this would look like as an equation. So I would have 2 times x plus 3 times y, 3 times the number of 3-pointers, and that would equal 30 points altogether. So that's my equation for this part of the problem. Okay, but we have more information now. So Derek tells you that the number of 2-point shots he made is 5 more than the number of 3-point shots. How many combinations can you come up with that fit this scenario? And right now we're not worrying about the total number of points, just what are some combinations that could work for the number of 2-point shots being 5 more than the number of 3-point shots. So go ahead and pause the video and come up with some possibilities for that would work. Okay, so let's look at some ways this could work out. So if he had 0 3-pointers, 5 more than 0 would be 5. If he had 1 3-pointer, 5 more would be 6. Notice that he can't have less than 5 2-pointers because that would be less than 0 3-pointers, which doesn't make any sense. Okay, so if I do 2 3-pointers, it would be 7. 3 3-pointers would give me 8 2-pointers, and so on. So those are the options for, well, some of the options. There would be more for knowing that there are 5 more 2-pointers than 3-pointers, okay? So how could we write an equation to model this situation? Well, we already know what our variables are standing for because x is the number of 2-pointers, y is the number of 3-pointers, so this becomes a pretty simple equation. The number of 2-pointers is equal to the number of 3-pointers plus 5. So 5 more 2-pointers than 3-pointers. Okay, so notice that all of the ordered pairs up here are going to work in this equation. If I put in 2 for y, 2 plus 5 is 7, I get 7 for x. So all of this data, or these points, will be true in this equation. But what we're asked now is to say which pair of numbers from this table would show Derek's actual score of 30 points. So what we need to do is go back and look at what were the options on the other table that might match this one. So I'm gonna put that one up briefly, and we'll see if we can tell which point that is. So what I'm looking for are values on this where the number of 2-pointers is 5 more than the number of 3-pointers. So in this first case, it's 15 more. In this case, it's 10 less. There's the same. This point, however, this 9, 4, notice that the number of 2-pointers is 5 more than the number of 3-pointers. Not true here and not true here. This one's actually 5 less, okay? So this 9, 4, notice, was on our other table. So let's go back and look at that one. So 9, 4 right here is where we have 9 2-pointers and 4 3-pointers, and the number of 2-pointers is 5 more than the number of 3-pointers. So this is the pair of numbers that we were looking for that satisfied both of those conditions. And so what we have here is something called simultaneous equations, also known as systems of equations. So there are 2 or more equations that have to be true for a particular xy value at the same time. So that's what simultaneous means, at the same time, or a system meaning a group of equations, basically. So let's look at Derek's situation. So what did he have? He had his total points from 2 and 3-pointers is 30, and he makes 5 more 2-pointers than 3-pointers. So those are the 2 conditions we have, and those lend themselves to 2 equations. So we are going to define our variables for both equations to be x to be the number of 2-pointers, y to be the number of 3-pointers, and these were the equations that we came up with. And so what you have here is some notation for a system of equations. We write them together and use brackets to show that we want both of these equations to be true at the same time. And we found that if we put in the ordered pair 9, 4, that those 2 equations will both be true. So if I let x equal 9 and I let y equal 4, and I go ahead and substitute those values into these 2 equations. So I'm going to put the x and y values into the blanks. X is 9, y is 4. I can see that both of these equations are true. 9 is equal to 4 plus 5, and 2 times 9, which is 18, plus 3 times 4, which is 12, is equal to 30. So both of those equations are satisfied by that one xy pair. So that would be our solution there. So let's look at the graph. So if I graph these equations, which you're going to be doing more of, you're going to be doing it in this lesson and actually more of it in lesson 25, this is what the graphs of those 2 equations look like. So if I look at x equals 5 plus y, these are all the points that satisfy that. Now I want to point out that for this problem, only the whole numbers could possibly be solutions. Okay, I can't make 5.5 baskets or 6.5 or anything other than a whole number. But fortunately, our graphs are crossing at a whole number location. So if you look here, you've got this point 9, 4, this point where the 2 lines intersect is at 9, 4. So what I notice here is that when x is 9, and that's the number of 2-pointers, and y is 4, the number of 3-pointers, that I get this intersection of these 2 lines. So it is a solution to both of those. So the ordered pair 9, 4 is a solution to that system of equations. Okay, now we're going to look at an example before we go on to your other exercises where simultaneous equations are used to make sense of a constant speed situation. So let's look at this one. Sandy and Charlie run at constant speed. Sandy runs from their school to the train in 15 minutes and Charlie runs the same distance in 10 minutes. So Charlie's clearly faster, right? Because the same distance in less time. Charlie starts 4 minutes after Sandy left the school. Can Charlie catch up to Sandy? The distance between the school and the station is 2 miles. Okay, so what we want to know is we know that Charlie is faster than Sandy, but Sandy has a head start and the distance to the school is only 2 miles. So can he catch up to her before they get to school? All right, so let's start making sense of this problem. All right, so let's write down our rates. So Sandy's rate is 2 miles in 15 minutes. And another way to think of that is to say that it's 2/15 of a mile every minute, or so 2/15 of a mile per minute. All right. And then Charlie's rate, which is faster, is 2 miles in 10 minutes. And that can be written more simply as 1/5 of a mile per minute. Okay, so just simple unit rates so far. So we know their unit rates and we know Charlie is faster. But Sandy has a head start, so let's look at what that will mean. So her head start, she's going 4 minutes ahead of him. So how far will Sandy travel in that 4 minutes? So in order to write these equations, I need to know where she's going to be when Charlie starts the race, and you'll see that in just a minute. So she goes 2/15 of a mile per minute, and in 4 minutes, if I multiply by 4 minutes, I'm going to get that she traveled 8/15 of a mile in that 4 minutes. So she's gone almost half a mile before Charlie even starts. Okay, so let's summarize that and give ourselves some more room. So Sandy can go 2/15 of a mile every minute. She gets a head start of 8/15 of a mile before Charlie. Charlie can go 1/5 of a mile per minute, and he has no head start. He starts at distance 0, at time 0. So if we want to put this in equations, I'm going to do it this way. So I'm going to say that y is going to be my distance traveled. So for Sandy, her distance traveled is 2/15 of a mile every minute. So I'm going to be multiplying that times the number of minutes that she travels. And then I'm going to add 8/15 of a mile because at time 0, when Charlie starts, we're going to call that x equals 0. So when x equals 0, this whole term here will be 0, and her distance traveled will be her head start right here, 8/15 of a mile. Okay, so that's Charlie's is slightly simpler. So Charlie, his total distance traveled, which is y, is equal to 1/5 of a mile per minute times the number of minutes that he is traveling. Okay, so what we want to know, we want to use these equations to find out if Charlie can catch up to Sandy within the distance between where they start and the school, or I mean to the train station. Okay, so on this grid are graphs of Sandy and Charlie's runs here. And so you can see, and I've written the equations down below, so you can see that on this graph, at time 0, Sandy has already gone slightly more than half a mile. So you can see that there. And Charlie has gone nowhere because remember, this is time, which we always put time on the horizontal axis. Distance traveled is on the vertical axis. Notice that if we go back in time, notice where Sandy's line crosses the x-axis at -4 minutes. So what this is kind of showing, this is her 4-minute head start, okay? If I moved this line over to here, it would show her at distance 0 at time, at time 0. But she got a 4-minute head start, so she's already traveled a certain amount. And she's going to keep traveling at the same rate. And we can see this is a straight line. Okay, so you can see at 2 minutes, after Charlie has gone 2 minutes, he still has not traveled as far as Sandy. But you can see down here that eventually Charlie's line shows that his distance traveled is further than Sandy's. So what we need to know is, did he make it within the 2 miles? Okay, so what we can do here, in the next lesson, we're going to graph these more accurately so that you can tell the exact point here. But we can't really, on this graph, tell the exact point, but we can see that it's at about 10 minutes, okay? So what I want to do right now is I want to check x equals 10 minutes in both of these equations and see how far they've gone. Okay, so if I put in 10 for x in Charlie's equation, I get 1/5 times 10. And we can see that in 10 minutes, Charlie would have gone 2 miles. So his distance is y equals 2, or 2 miles there. Now let's put in 10 for the time in Sandy's run. So this is 10 minutes after Charlie starts, right? So she's actually been running for 14 minutes, but it's x equals 10 is our time on this graph. Okay, so the way we've graphed it, at x equals 10, Sandy will have gone 2 fifteenths times 10, which is 20 fifteenths, plus 8 fifteenths is going to be 28 fifteenths of a mile. So I want you to look at that fraction and notice that she has not quite made it to 2 miles where Charlie has. So Charlie is at the train station and Sandy is slightly behind him. So it was somewhere right in here that those graphs crossed. And these graphs might be not be drawn super accurately because we have no grid lines here. But we can see from evaluating these two equations for x equals 10 that Sally has not quite made it. So Charlie did catch up just before 10 minutes, just before they'd gone 10 minutes, he caught up and overtook Sandy. Okay, let's look at exercise 4 that you have in your notes, and we'll do this one together. I'll read it. Efren and Fernie are on a road trip. Each of them drives at a constant speed. Efren is a safe driver and travels 45 miles per hour for the entire trip. Fernie is not such a safe driver. He drives 70 miles per hour throughout the trip. Fernie and Efren left from the same location, but Efren left at 8 a.m. and Fernie left at 11 a.m. Assuming they take the same route, will Fernie ever catch up to Efren? If so, approximately when? Okay, well, hope you realize that since Fernie is traveling at a greater rate, he will eventually catch up. But the question is, when will he catch up? How long will it take him? And we can use a system of equations to figure this out. All right, so part A asks us to write a linear equation to represent Efren's constant speed, including his extra travel time. All right, so his rate is 45 miles per hour. And he's going 45 miles every hour on this trip. But he has a head start. And so let's figure out, where will he be when Fernie takes off? So when Fernie takes off, it will be 3 hours later. So if he goes 45 miles per hour for 3 hours, that's 135 miles. So that's his head start. That's where he's going to be at what we're going to call time 0. Okay, so let's look at our variables. So y is going to be the total distance traveled, and x is going to be the time in hours after Fernie starts. Okay, so we're not going to start the clock until they're both driving. Okay, so at 11 a.m. So hours after Fernie starts. So what that means is that when I go to write the equation for the distance that Efren travels, I'm going to have to take into account the fact that he goes 45 miles per hour times the number of hours. That's going to give me that distance. But he has a starting location. So I have to add 135 miles for him. So let's check this. So at time 0, which is when Fernie starts, at time 0, 45 times 0 will be 0, and my distance will be 135, and that's what we want. So that's his head start right there, 135 miles. Okay, so let's look at another way that we could have set up Efren's equation. So there are multiple ways to set these up, and even other ways you can think about how to make this time differential mesh. But anyway, let me show you another way to think about this. So we're still going to let y be the distance traveled, and x be the time after Fernie leaves. So from the time from 11 a.m. And so if you think about it, the time for Efren, the time he's been traveling, will always be 3 hours more than what Fernie traveled. So we can call his time, instead of calling it x, we can call it x plus 3. And I'll show you how this works out. So we can set up his constant rate is y, y miles, and x plus 3 hours. And that we know is 45 miles per hour. So 45 over 1. And by multiplying that out, I'm going to get that y is equal to 45 times x plus 3. And using the distributive property to multiply that 45 by the x and the 3, we get y equals 45x plus 135. So you can see his head start on here just by setting it up, thinking of the time being x plus 3. So as you do these problems, do them however it makes sense to you, but always check your equation to make sure it makes sense within the problem. Okay, so part B asks us to find Fernie's equation for this trip. And so his is a little bit easier because he doesn't get a head start. So for Fernie's equation, y is, again, the distance traveled, and that's going to equal his rate, 70 miles per hour, times the number of hours that he travels. And that's it, just y equals 70x. So if he travels for 3 hours, he's gone 210 miles. Okay, so part C says to write this as a system of equations. So for part C, we're going to use the brackets, and we're going to write each equation within the brackets. So the brackets tell us that in order to find a solution, it has to be true in both equations. So, so we're going to find an XY pair, an ordered pair, that is true for both equations. So what we want to do now is look at the graph, because that's going to give us some good clues as to about the time that Fernie may have caught up. Okay, so this is something that you can definitely work on independently and come back and check your work with the video. Okay, so let's plot some points first for Fernie's trip, because that's a little bit simpler, and then for Efren. Okay, so here's some points, and I'm going to do Fernie in purple. So at 0, at time 0, he's gone 0 miles. So I put on 3 hours. 3 hours is 210 miles, and at 5 hours, 5 times 70 is 350. So he's gone 350. So we can draw a line between those points, and that shows Fernie's constant speed of 70 miles per hour. And you can actually see his constant speed right here. 1 hour should be crossing at about 70 miles. So roughly halfway between the 50 and the 100. Okay, this is a pretty rough graph, roughly drawn graph. Okay, so let's now plot Ephraim's trip, and we'll do that one in green. So here are some points for his trip. So the first one I plotted was at time 0. So this is, remember, this is 11 a.m. This shows Fernie's head start of 135 miles. So that's our y-intercept, right? It's kind of where it crosses the y-axis is sort of time 0. This shows Ephraim's head start of 135. Okay, and then at 2 hours, he has gone 2 times 45, which is 90, plus the 135. So that comes out to 225. So that was a pretty easy point to plot too, right? Halfway between 200 and 250. And then I calculated for 5 hours, he would have gone 360 miles. So at 5 hours, notice they're really close together, but Fernie's still ahead. Okay, so we'll connect those dots with a line just to show. So this shows Ephraim's constant speed, and you can see his constant speed is less by the slope. His slope is not quite as steep as the other line. I want to point out another point that ends up on this graph, and that's this one down here. So this is where x is -3 and y is 0. So what this shows is the 3-hour head start that Ephraim took. So he was traveling for 3 hours, going up, 45 miles per hour before Fernie started. Okay, so it's Ephraim's head start right here. So 3 hours, and here's the 135 miles. Okay, so there's the two graphs. So what we're looking for is where they cross, and where they cross is going to be the place where the time and the distance are the same. So we've got a point here between 350 and 400 miles, and somewhere between 5 and 6 hours where Fernie finally catches up to Ephraim, and then from then on he would be out in front. He would be ahead because his rate is greater than Ephraim's. Okay, let's look at exercise 5. In exercise 5, we have, again, 2 people running at constant speeds, Jessica and Carl. Jessica can run 3 miles in 24 minutes. Carl can run 2 miles in 14 minutes. They decide to race each other. As soon as the race begins, Carl trips and takes 2 minutes to recover. Okay, so we're going to be asked some questions about this situation, but what we want to do is first define our variables and write some equations. So to define our variables, once again, we're going to let y be the distance traveled. Always we're going to have distance traveled on the vertical axis. And so x will be the time. And the way I'm going to do this one, although you could do it a different way, I'm going to let x be the time from when Carl recovers. So it's going to be as if Jessica gets a 2-minute head start. So it'll be like our other problems in that way. So if I want to then write Jessica's equation, her constant speed is going to be her distance traveled over the time. And the time for Jessica is always going to be x plus 2 because she has that 2-minute head start. And that's equal to her constant rate, which is 1 mile in 8 minutes. So notice she went 3 miles in 24, so I've just simplified that to 1 mile in 8 minutes. So multiplying both sides of that equation by x plus 2, I'm going to get our equation it's going to eventually be in slope-intercept form. So multiplying out the 1/8, so we've got y equals 1/8 x plus 1/4. I'm getting that from 1/8 times 2. Okay, so that's Jessica's equation. And now Carl's equation is a little simpler because he's starting at time 0. So his distance traveled is y, his time is x, and that's equal to 1 mile in 7 minutes because he can go 2 in 14. So we can see that Carl is faster than Jessica because 1 in 7 is faster than 1 in 8. So his equation is y equals 1/7 x if we multiply both sides of that proportion by x. Okay, so we have the two equations, and now we can set up our system of equations. Part C asks us to write the system of equations. Okay, so here's our system of equations, and I'm just going to add the brackets there to show that we have a system. And when I did that, my points came up too. So I've already started plotting Carl's run. Y equals 1/7 x. So I put 2 points on here, of course, when x is 0, y is 0. And that point is right here. I chose another one that would be easy to find. At 7 minutes after he gets up, he will have gone 1 mile. So there's another point for Carl's graph. And I can draw a line through those 2 points, and we can see that slope of 1/7 going on there, and just notice that the way the axes are numbered here. These are going up by 2/10 of a mile here. So I've got 1 mile in 7 minutes. 1/7 is the slope of this graph. Okay, so Jessica's run, she gets a head start of, she's going to be 1/4 of a mile in by the time Carl even gets up, because she's been traveling for 2 minutes, and she goes 1/8 of a mile per minute. So she's going to get a little bit of a head start. So let's look at some points for her graph. Here is her 1/4 of a mile head start right here. That's going to be 0.25 at time 0, because the time 0 is when Carl gets up. See, at time -2, she's at 0. So there's her 2-minute head start where she's already running. And let's see, so I chose 6 minutes because in 6 minutes she'll be at 1 mile. 6 times 1/8 is 6/8, which is 3/4 plus 1/4 is 1. So there's my well, really third point there. So notice that at 6 minutes, she's still ahead. At the 1 mile point, he has not recovered. He's not caught up with her yet. So let's look at her line. And notice that her slope is not as steep as it shouldn't be, because her speed is slightly less than his. And but we do notice that out here, eventually, Carl in green overtakes her. So it's right in this area where he starts, he's ahead of her a little bit there on the graph. His distance traveled is greater in the same amount of time. So there's so much you can tell from these graphs, but we're really looking for this intersection point right here. So at 14 minutes, they've both gone 2 miles. Okay, so let's look at part E. It says to use the graph to answer the questions below. So I've reproduced the graph on the screen, but you have yours in front of you as well. This question asks, if Jessica and Carl raced for 3 miles, who would win? Explain. Okay, so I'm not sure if, I'm assuming they're keeping the stumble in mind when they talk about this, but either way, I'm gonna explain my thinking on this, and you could explain yours. Hopefully you have. Jessica would take 24 minutes to go 3 miles, and because she goes 1 mile in 8 minutes, or 3 miles in 24 minutes is what they said. Carl goes 2 miles in 14 minutes, so it would take him 21 minutes to go the 3 miles. So Carl would take 21 minutes, and that's assuming he didn't stumble, but he did stumble. So that basically adds 2 minutes to his time. But even with the stumble, we can see that if the race was 3 miles long, Carl would still win, even having stumbled the 2 minutes there. Okay, and so then the second part of that says, at approximately what point would Jessica and Carl be tied? And we talked about this just a minute ago, and we saw on the graph we drew that at 14 minutes after Carl gets up, he will have gone 2 miles, which makes sense since he goes 1 mile in 7 minutes. And at that same time, Jessica will also have gone 2 miles. So this is the point where their lines cross, and this is the point where they would be tied. So we could say 14 minutes after Carl gets up, they are both at the 2 mile mark at 2 miles. And that's where their paths would cross again. It kind of makes sense because think about it. 16, if she goes 1 mile in 8 minutes, she's actually been traveling when he's been gone for 14 minutes. Jessica's been running for 16, so that's 2 miles for both of them. Okay, so I think these are challenging problems. There are just 2 of them for you to do in the problem set. So I encourage you to struggle with them for a while and then check your work against the answer key. Noting that there are different ways to think about this, but if your conclusion ends up being the same, even if your equations look a little different or your graph looks a little different, you're still on the right track. Okay, be sure to look over your lesson summary. We've talked about that a system of equations or simultaneous equations are sets of equations, 2 or more, that are graphed together, and the solution is an ordered pair that works in both equations at the same time. An example is given here that you can look over. And be sure that whenever you write a system of equation, you include brackets. The brackets show us that they need to be solved simultaneously or solved together. Okay, good luck with the problem set and the exit ticket, and we'll see you back here for lesson 25.